Okay, here 13.6. This one is about mutually exclusive. Recently we did one about independent, and the other big term you have to think about when you're deciding what to do, how to perform your calculations and probability is this idea of mutually exclusive. These are very common words we use all the time in AP Stats. Independent events versus mutually exclusive. They're very different. This will be the lesson you remember where we learned about Venn diagrams. So I put this little highlight here. Venn diagrams is kind of the big takeaway from this lesson. Okay, so what does mutually exclusive mean? Mutually exclusive means they can't both happen at the same time. Like, you can't be in ninth grade and 10th grade at the same time. So we're trying to find like probability of a ninth or 10th grader. We know that those two things can't happen at the same time. There's no such thing as and. When and doesn't make sense, then we're talking about things that are mutually exclusive. You can't have a heads and a tails on a coin. You can have things that are not mutually exclusive. Now, after all those examples, like if we're talking about rolling a die, you could say a number greater than 3, and you could talk about an even number. Like, yeah, it's possible for both those things to happen at the same time. If you roll a 4, that's both greater than 3 and even. But you can't have heads and tails on a coin. You can't have a 5 and a 6 on a dice. So if they are mutually exclusive, then here's the big so what. Why do we care about that? Well, when things are mutually exclusive, that means you can add them. Then you can change or into an and. This should feel kind of like the thing we did a couple of lessons ago with independence. If there's independence there, and here means multiply. This is the same type of thing. If you know it's mutually exclusive, so that's the big what if, that's the big assumption you have to be sure of first. Then or means plus. Sometimes they use this symbol for or. It looks kind of like a little U. It actually stands for the word union. The union of those two sets is just add them together. You can only do that if it's mutually exclusive. If they're not mutually exclusive, if there's a chance that things could be both A and B at the same time, then this will overestimate the probability, and that's not good. Okay. Oh, by the way, if you're going to use this symbol for or, we probably should have told you this too. Back in those days when we were doing the, when we were doing the intersection, that you can think of as kind of like or. We're learning that today. And you might see this symbol upside down. That actually stands for and. That stands for intersection. Okay, symbol comes from the word U for union, and then they're kind of opposites of each other to think of or and and, so they just flip the U over when they're talking about and. I don't think we did that back in those times, but you might see that. Oh, here's an and. Oh, right there. Okay, great. All right, events that are not mutually exclusive may occur simultaneously. Oh, here's like what I was just saying. Rolling an odd number and rolling a multiple of 3, that could happen at the same time. So since that won't work with adding, they make a bit of an adjustment. Then you have to be a little bit more careful and say, well, yeah, the probability of one or the other happening is the same as adding them both together, but then you have to subtract out the number of cases or the probability that they actually do happen at the same time. We'll see why this works, why this adjustment makes sense when we start doing Venn diagrams. There's also a similar one you can do. You can make an adjustment to the multiplication one with independence if you know they're not independent, but I don't think we are going to study that this year. Okay. An event either occurs or it doesn't, if you think about it. Probability of A not happening is mutually exclusive to the probability that A is going to happen. It can't both happen and not happen at the same time, so they're mutually exclusive. So we should be able to add them up. It's okay to figure out that probability as adding. And of course, A, and I'll write it up here what I'm talking about. Probability of A has to be completely mutually exclusive to the probability of not A. These two things can't happen at the same time. And what we're saying here is if they're mutually exclusive, then you can add them. Well, what should they add to? The probability of A happening or it not happening? Well, either it has to happen or it's going to have to not happen. This or, probability of A or mutually exclusive mutually exclusive plus, probability of A or not A happening has to be 100%. It either has to happen or it doesn't happen. There's no other possibilities, and they're mutually exclusive. They should add to 1. Rearranging this just slightly, we know we can figure out a way to write probability that A doesn't happen is 1 minus the probability that it does happen. They just subtracted this on both sides of this equation to get this. Another way to write this, and this is a little more, well, it's faster for one thing, and it's accepted, is they put a little prime there. They put a little apostrophe there to stand for not A. So I kind of like this better. Probability that A doesn't happen is 1 minus the probability that it does happen. Okay. Venn diagrams. So yeah, this is the big thing for today. Venn diagrams, you've probably seen before. This circle represents all the cases where A can happen. This circle for B represents all the cases where B can happen. This box on the outside is a representation of the sample space. So here's the universe of all possibilities. Some of them fall under A, some of them fall under B. And if you draw it this way, you're talking about mutually exclusive. This is a mutually exclusive Venn diagram. Most Venn diagrams don't look like that. Most Venn diagrams show some kind of overlap. So here's set A. Here's all the possibilities where A can happen. Here's all the possibilities where B can happen. And you notice we've got this little football in here that represents the intersection, where there's some chance for both of them to happen. And then this white space on the outside is represents, or this is where you would think about there's cases that neither one of those happens. They're outside A and they're outside B in the sample space. Certain regions of this may actually have nothing in it. That's okay. I don't know why they have one bigger than the other. There's really nothing implied by the fact that A is kind of smaller than B. Usually they don't draw them smaller like that. Usually they draw them the same size. All right. This one is what they're shading here. Is they're shading the entire snowman. They're shading the probability that A or B happens. So in other words, it's considering any of the possibilities that could land in A or in B all at the same time is kind of our success criteria here. So for that, you would shade everything in both of them. So I shade the entire circle A, the entire circle B, and it's all kind of the same level of importance. Was this trying to show me that? Yeah, the intersection is technically just this thing in here. The intersection is really only that. This red part I just drew is the intersection. The fact that this is shaded and this is shaded just kind of helps us to know, okay, we're looking for the doubly shaded stuff when we want this intersection. Here we just want the single shaded stuff for the or, because it could be an A outside B, it still counts in or. Being in B outside A still counts as or. Being in both still counts as or. Like if they asked you, are you in 9th grade or are you in geometry, and you were in both, you wouldn't say no. No, I'm not in 9th grade or geometry. I'm in 9th grade and geometry. Well, people don't talk that way. If you said, are you in 9th grade or are you in geometry, and you were in both, you would also say yes to that question. So we also shade the intersection when we say union. Okay, notice the intersection is part of that, yes. So if we were to figure out the probability, if we were to calculate what's the probability of this whole big blob, you wouldn't want to just add the two circles. Like say the probability of this is, I don't know, 10%. There's a 10% chance that a randomly selected person at the high school is in geometry. And there's a 25% chance that the randomly selected person is in 9th grade. So what's the probability that you're in one or the other? Well, we can't just say 10 plus 25. This would not be good for 35%, because it would count this little thing twice, and that would be a problem. We have to know what is maybe actually right in there. It has to be smaller than 10, it has to be smaller than 25. Let's say it's 3%. There's 3% of the high school that's in both 9th grade and geometry. This is probably a bad estimate, but notice if I added this 10% and this 25%, I wouldn't have 35% of the people, because I would have counted this 3% of the people twice. You can think of it this way, because I'm trying to figure out how, what's the probability that I find someone in here. Or you could think of this as numbers of people too. Anyway, if I count A first, I've counted these people once, then what do I really have to add on to that to figure out the area of the outside, the whole set together? I add on 10% plus like this cookie with a bite out of it, which if you think about it is really just an additional 22%. So it's really 10 plus 22, or in other words, the way they're going to do it on the next page is add the 10%, add the 25%, and subtract out the 3, because you've counted it twice, and we should only count it once. Yes, it counts, but it only counts once. If we count it as part of both big sets, when we add them, we would have counted it twice. So we take out once to make it fair. All right, what if we had exhaustive events? Exhaustive events means that when you find the probability that one or the other one happens, it has to be 100% total. So it's kind of like the same thing as saying, well, the probability that A doesn't happen would mean we're talking about the exact same possibilities that are B happening. So, and between A and B, we will represent the entire sample space. Venn diagram of exhaustive events. Well, we couldn't really draw A and B as circles like that because we don't want anything to be out here. We want A and B to be so large that they fill this entire, to make a representation of it. We want them to fill the entire space. So one way to do that is just say, okay, this block represents A and this block represents B. So together, they cover everything. Now, could there be some intersection between A and B? I suppose there could be some intersection of A and B. So we could maybe draw that. The thing is, we have to make sure that A and B together represent 100% of everything. So that would be if they were mutually exclusive. If they weren't mutually exclusive, I don't know. I guess I could imagine something like this, where this is the set of B and this is the set of A or something like that. Oh, we got some on the outside of both. We don't want that. Let's get rid of that. So the set of so A is like that. So maybe something. It's hard to read what I mean there. Let's do it this way. Let's shade that. So the set A, I'm gonna have it be this yellow color. A is all of this stuff. And again, there's nothing on the outside, so it's all of this. And B is all of this green stuff. It goes all the way to the edge. There's everything represented there, but it also includes some of the A possibilities. So you could draw it that way too. So there's some overlap. This is green and yellow, if you can tell. I could do this and show you. Yeah. A was a set that was, whoa, maybe I can't. A was a set that was that big, B was a set that was that big, but A or B, the probability that A or B happens, you can't escape that. It's going to be 100%. All right, back to the dice. Find the probability of getting a 6 or 7 when rolling 2 dice. Okay, or, so we have to ask ourselves, we're going to do or, can we add those? How do we add those? Do we have to worry about mutual exclusivity? Well, is it possible to roll a 6 and a 7 at the same time? No. So we can just simply add them. Probability of rolling a 6. I'm just gonna find them all here. There's a 6. 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 Of course, these are yellow. Sorry, they're green on top of green dice. And here's all the 7s right here. I missed that one a little bit. So it's all those all together. How many is that? 6 to roll. Probability of rolling a 6 was 5 of the 36. Probability of rolling a 7 was 6 out of the 36. And since this is or and it's mutually exclusive, we can actually just add them up. 6 or 7 happens 11 out of 36 times. Give the two-way frequency table. Given this two-way frequency table that shows types of painting and medium used, find probability of oil, painting, or portrait. You know what I would really like to have on this table is the margins. I don't have enough room. I have to shrink this up so I can draw the margins. It'd be really nice to see this. So let's put totals in there for this. Total, column, total of total row and a total column and then a total in the outside there. Okay, so this is total across here is 12, total this way is 6, total number of acrylic is 6, total number of pastel is 6. So that's 12, 24, 30, okay? Total number of landscape, looks like it's 11. Total number of portrait is 10. This better be 9. 4, 8, yeah, it's 9. Great. So find the probability of oil painting or portrait. So if we're going to select a randomly selected piece of art here, what's the probability that it's an oil painting or it's a portrait? Well, I would think of this way. Like the probability of an oil painting is all of these. Probability of a portrait is all of these. We don't want to count this 3 twice, though. So one way we can do that is, since these are not mutually exclusive, we have to follow that rule that says you add the 2 up and then subtract out the overlap from that one. All right, so we're back to here. Probability of oil was, where's the oils? Right there, 6 out of 30. Probability of portrait was 10 out of 30. But the probability of both was the 3 out of 30. So we got to subtract that. So this thing up here, I'll just put an equal sign for this. Probability of oil painting or portrait is the 6 plus the 10 minus the 3 out of 30, and so that's 13. Another way to think about that is, okay, let's count all the numbers in this yellow zone, in all these yellow zones, but I can only count them once. So 1 plus 5 plus 3 plus 2 plus 2 plus 0, that should be 13. Is it? Yeah, it is. That's good. Okay, can I get rid of that highlighting now? Because I don't want to think about that. I'm going to go to the next thing. Okay. Probability of still life and acrylic. Well, still life and acrylic is just in one place. Still life and acrylic, we're good at reading these out of the table by now. To be both, it just has to be one of those. So that's just 1/10 after you reduce it. Okay, I'm going to run out of time. See you in part 2.